Okay, so our first talk today is going to be by Benjamin Fele on generative adversarial networks and their applications using PyTorch. And Benjamin is a PhD student at Faculty of Computer and Information Science at University of Ljubljana, and he's working at Jozef Stefan currently. And he has gained experience in different fields of machine learning, from cognitive modeling at University of Bratislava and meta learning at UC Berkeley to virtual Tryon at Faculty of Electrical Engineering. He's currently researching algorithmic curriculum generation for robotic motor learning, and has a recent history of involvement in multiple projects in collaboration with Kapelica Gallery and Osmo, which I think that is also mentioning some of those projects today in his talk, right?
Yeah, that's true.
Great, looking forward to that. So we can all see your screen. Okay, thank you. Let's begin.
Okay, sure. So yeah, as mentioned, I'm gonna talk about generative adversarial networks and then their applications. I'm gonna talk less about PyTorch, and I probably won't concentrate on code samples as much as I had hoped to. But yeah, it kind of all boils down to the project FlatGaze, which is authored by Matej Hiltz. It is an artistic project that kind of, in a nutshell, or in a very on a very concrete level, aims to generate images of exhibitions, and it uses generative adversarial networks to do that. Now, I will kind of lead my way to actually to the point where I'll actually say a few more words about FlatGaze, and I'm first going to start by introducing some preliminaries. Like I'm going to start with artificial neural networks, like what they are, maybe how they work. I'm going to move on to generative adversarial neural networks, which are kind of a subset of neural networks in the first group. I'm going to speak about some applications, which I think is cool because it helps everyone kind of imagine how they are used. And finally, I'll get to FlatGaze, where I'll describe a bit more in detail how it works, how it was implemented. And finally, if there's time and depending on your interest, I would also like to show you some code samples, but we can also just have a discussion. I think with the first 4 points, I will easily reach 30 to 40 minutes, and then depending on how you feel, we will kind of continue. Yeah, so let's first start with artificial neural networks. This is, for those who might not know anything about artificial neural networks, I guess a good metaphor is to compare them to a human brain or human central nervous system, in a sense that artificial neural networks are also comprised of neurons that are connected together. They form a network, and by activating some of these neurons, we kind of get propagating activations throughout the whole network. Now, the neuron in this case is kind of an abstract term. In practice, it's all about multiplying numbers or multiplying matrices. But I think for someone that maybe doesn't know anything about artificial neural networks, it's kind of cool to imagine them as interconnected neurons. So here on the right, we see like a schematic representation of how an artificial neural network would look like. And it has a few properties that I want to talk about. First of all, it receives an input and it gives an output. In that sense, it serves as kind of a function. And the idea is that with neural networks, we want to approximate mathematical functions to yield some kind of output depending on the input. And another thing you might see is that it's these neural networks. Let me enable my pointer. These neural networks, or at least this particular one, is comprised of layers. And since this is a fully connected neural network, these layers are fully connected. So every node, you can imagine this as a neuron, or you can imagine this as some kind of number that denotes the weight of this node, is connected to all other nodes on the next layer. And then these activations kind of propagate through the whole network. So yeah, as I mentioned, this is a certain kind of neural network which is fully connected, or dense neural network, because it has densely connected layers. And this problem that this network would solve here, or this kind of schematic would represent, is a classification problem, which is just one very small set of problems that neural networks can solve, and it kind of and it's concerned with categorization of the input data. But it doesn't have to be that way. First of all, you have many other types of neural networks of different architectures, which can kind of be grouped in three other groups. One are convolutional neural networks that are particularly useful for signal processing, or just kind of understanding understanding patterns in signals. You have long short-term memory, which is concerned with sequences of data, and you have lately very popular self-attentional neural networks, which have some kind of attentional mechanism that helps them to narrow down the relevant information and as it propagates the activations in the network. This last group of neural networks is particularly popular in, for example, text generation. Maybe some of you have heard of GPT-3, or even before that, BERT, and so on. These networks use self-attentional mechanisms. Then another kind of view on machine learning in general, not just neural networks, is also through what kind of data and what kind of problems they're trying to solve, where we have supervised learning, unsupervised learning, reinforcement learning. This is like a common distinction, or a common introductory distinction that is made all over the internet and in some courses. And the idea is that in supervised learning, you have data and you have some labels or some values that you want to relate this data to. For example, that typical example would be classification problem, but also regression problems, like predicting the temperature in next year based on temperatures in last 10 years, for example, where we have like continuous output. You have unsupervised learning, which aims to kind of find underlying patterns in data and doesn't have labels. That's the biggest difference to supervised learning. And one good example of that would be, for example, clustering, that kind of just finds groups of data that are closely together, and that tells you more about more about the data itself. While lastly, you have reinforcement learning, which is more of having an agent performing actions in some kind of environment, going through different states, and the goal there would be to kind of teach, to kind of learn the actions that maximize some kind of reward. Now, these three categories are all categories that span, that are wider than neural networks themselves. But neural networks are just kind of one particular way of solving some of these problems that these categories entail. A distinction I prefer actually is, on the other hand, this one, which divides neural networks or modeling in general into generative and discriminative, where in generative case you have input data and you aim to learn the underlying data distribution, while in discriminative neural network you have you also get some input data, but you want to learn the boundaries. So a typical example would be, again, categorization versus, in generative case, for example, generation of image data, of images. So this distinction, I think, will come in handy a little bit later when we talk about generative adversarial networks. But first, I want to briefly stop and say a few words about how neural networks are trained. So this is the image from one of the earlier slides, and it's all fine and well. You have an input and you get an output, but the problem is that this doesn't say much about how one would train such a network, because I do not remember if I've already mentioned it, but these weights in the network are initialized randomly. So for an input, you would get random outputs, which is not very useful. And for that reason, when training the neural network, this is really an important, for me, the most interesting part, you add another function on top of the neural network called the loss function, which outputs just single value, and this value simply correlates with what we want our neural network to do. And I want to point out this graph on the right here. And you can imagine being in a room, for example, and maybe feeling a little bit hot. And you go to the temperature dial and you turn the knob a little bit, and that changes the temperature for a certain amount. And you wait a bit, you see if you feel any better, if it's more cozy for you. And it turns out you're still not quite at the sweet point, and then you make another step, you turn the dial again. You repeat this procedure until you feel just right. That's where this kind of minima in the function that you want to optimize is. Now, in the real life example, it's maybe a bit hard to say what the real loss function would be, but in mathematical sense, it is often noted as, let's say, a difference between some target outputs and the current outputs of the neural network. And we simply want to, for every, if we are at some point on this curve, we simply want to find the derivative to move in the direction that minimizes the loss. So, and yeah, that's kind of the core idea of how neural networks get trained. But of course, they do not get trained just in one dimension, like it's denoted here, where you would have just one weight and you would kind of slide this weight left or right depending on how the loss is changing. Usually, neural networks have millions of parameters, millions of weights, and even in two-dimensional case, you can imagine being on a hill and having essentially two directions to move in. And for each of these two directions, you could calculate the derivative and then move in such a way that would get you to the bottom of get you into the value. And you can probably still imagine doing this in two dimensions, but in million dimensions, it's like, or in millions of dimensions, it's like going downhill going downhill in a very complex environment, if you want. And yeah, that's really what all this gradient descent is about. You calculate direction in which you would want to move in respect to the loss you have, and kind of just change the weights a little bit to move into that direction. So now I think the worst part of this presentation is over, in a sense that this was, I think, the most theoretical part. And I think the generative adversarial networks become a little bit more fun, and I'm going to talk about them now. So generative adversarial neural networks are actually not one neural network. There are two neural networks. One is called the generator, and the other one is called the discriminator. You maybe remember this terminology from one of my earlier slides. And they play a game. They play a mini-max game where they each want to outperform the other. So the generator generates output based on some latent vector, which is usually sampled from normal distribution, but that's not really important. While the discriminator judges whether generator's output comes from the data set, or whether it was generated. So the discriminator has to judge whether the data that the generator outputted is real enough. Or in other words, they both begin by knowing nothing. Discriminator learns to distinguish real and fake outputs, and in the beginning that's really easy because generator is just, for example, generating some random images, and while on the other hand we have a training set of faces or cats or whatever we want to generate. But since the discriminator learned to distinguish these two groups of data, the generator receives feedback about its outputs and improves. And it's all done through gradient descent that I talked about earlier. And then since the generator is improved, the discriminator has to learn again how to distinguish them. And it's kind of an endless cycle until they both converge. This is more graphical representation of that, where you have this discriminator that I've talked to you about, which receives two kinds of data: training set that in this case I think it has it contains some characters, but it could be anything. You know, in the case of flat gaze, these are the images of exhibitions. While on the other hand, you have a generator that generates some kind of image, and in kind of the first step, the discriminator is trained to distinguish between the two, while in the second step, the generator, based on the error, based on how far, based on from how far its inputs, its outputs are from the real images, updates its weights to kind of match the training set distribution better. And another important thing is that in order for a generator to kind of produce variable output, it receives noise that I've talked about to you a little bit earlier already. It receives this latent vector that for every different point that for every different value outputs a different image. And the third thing is I wanted to avoid equations, but this is kind of the beauty of it, that I try to explain this to you in three different levels. You have this equation that actually explains what we are optimizing, and you have a discriminator and you have a generator, which are denoted by B and G. And first, if we look at the discriminator, we want to maximize this term here, and we also want to maximize this other one here. And discriminator outputs a probability that the data is real. So when we show it real data, which is X in this case, we want this to be high. We want this to be as close to 1. While on the other hand, if we show it the output of the generator, we want this to be low. That's why this is 1 minus this value, and this kind of serves to train the discriminator to actually distinguish between samples. While the generator, on the other hand, has to minimize this whole term, this whole equation. And for the first part, it doesn't need to do anything because there's no generator here. But for the second part, we want this term to be as low as possible, meaning that the discriminator has to output values as close to 1, because 1 minus 1 is very close to 0. And if we are minimizing that, we want the generator's outputs to kind of be able to fool the discriminator. Okay, now I want to say a few words about latent space, which is a very nice property of generative adversarial networks. And nice property in the sense that similar latent codes produce similar outputs. And this is like a very wannabe latent vector. And this latent vector represents the point in the latent space. So every time you sample these points, if you sample 2 points that are close together, like for example in terms of Euclidean distance, they are bound to produce similar results. But similar in what way, you might ask? And I'm not sure I can answer that question very well for you, because it depends a lot on the data, and it also depends a lot on how generator is trained, what kind of architecture it has, and so on. We'll talk about this a little bit later. But kind of the overarching notion is that in order for the generator to generate realistic samples, it has to produce outputs from compressed representations, because that's the only way it can encode enough details. So the only way it can encode enough details is by grouping these similar samples closely together, because otherwise these latent vectors just wouldn't carry any information about how the output should look like. And what this brings us to is a more applicative part of this presentation, and that is first of all editing in latent space, which I think is extremely cool, and I know it opens up a lot of possibilities, not just for generation but also for image manipulation. And one very famous approach is to edit, for example, images across some attribute, for example, age or gender, and so on. So what you would do is you would kind of try to find the line that separates young people from old, in the case of age, and you would take a latent vector, you take a point in this latent space, and you would kind of move orthogonally to that separating line. That would kind of make the person on the image, for example, older or younger. What this also allows is changing multiple attributes at the same time, or because sometimes these attributes are entangled, it enables to just change one and not the other. Note that you need to know in advance what kind of, for example, how does an old versus young person look like to actually do this, but it's really cool, and it's widely used in I think in many like popular apps, like I think it was Face app a few years ago, that I'm not sure if it used this particular technology, but used similar ideas, where you would kind of make somebody look older, or make somebody look more male, or whatever. And this could be one of the techniques to do that. The other use case I want to showcase is video generation, and particularly I think it's quite popular with deepfakes. But it's much more than deepfakes are much more than just deepfakes. They enable to kind of generate any kind of video, and this particular approach doesn't kind of describes how generator doesn't just have to accept the latent vector, but it can also accept, for example, a segmentation map that you can see right here, and then based on that, and together with the latent vector, it generates the outputs, which can be for two latent vectors completely different, but still have the same kind of semantics. You know, the road stays the road, the car on the image is on the same place as in both cases. But the idea of generator and discriminator here kind of playing this mini-max game, kind of trying to outperform one another, stays very similar as with still images. Less one of the more commercially viable use cases I want to talk about is also virtual Tryon, and these are the results from one of the projects I was part of, and that got me into generative adversarial networks in the first place. And here the problem is actually quite simple. You don't, but instead of, so the problem is quite simple in the sense that you get a picture of a person and you get a picture of a garment, and you want to dress up the person in that particular garment. So here it kind of shows that not only segmentations and latent factors, but also the garments themselves can be an input to the generator, and then we have to change the discriminator a little bit to kind of check if the outputs of the generator are actually the garments we want the person to wear. But these are all kind of, I think, yeah, as I've said, commercially viable use cases. But on the other hand, what generative adversarial networks are very popular for is also just generating art or maybe some fun things. And I've picked three here. One is Zizi's Cabaret, I think it's called, where they essentially used the technique from here to produce people dancing and yeah, people dancing and singing in the cabaret, and this is yeah, and this is, as you can see, this is not like the highest quality of results, and that's often how it comes out in practice, especially in art. It may even be desirable, but yeah, you can observe the results right here. On the other hand, you have, I find this kind of funny, you have some following in terms of generating high resolution anime girls. And I think this one is called, this waifu does not exist. I hope you can see this. And it essentially generates images of anime girls in high quality and some accompanying text that kind of gives the backstory, all done with generative adversarial networks. And lastly, you have ArtBreeder, which is another interesting project which doesn't just generate images, but enables you to change, or maybe I can show it, right? So you have, for example, this image, and you can, similarly to how I described before, you can say, okay, I want less of red sky, and it generates in real time a different image. And what it allows you to do is this changing. This is not going to work. Okay. What this changing allows you to do is, because I have to click this, what this changing allows you to do is kind of look at the family tree of a particular image. It's like, and then you can compare like how different images were evolving through time. And that brings me to the coolest project of them all, which is Flat Gaze that I was intending to talk to you today. And as mentioned, this is a project by entailing, and it's an Instagram-based project. And in the background, you can see some of the generated images. You might find them weird, but maybe just remember that the idea is not to generate the main point is not to generate the most realistic images ever. That's the first point, but the other thing is also that the data this generative adversarial network was trained on is it has a certain aesthetic. It's not just exhibitions in galleries. You can see that many of these images are kind of placed in a room, but also of particular objects. And what is art without giving you some context? And I'm not gonna explain Matej's artistic vision here. I don't think it's my place to. But one thing that really resonated with me is this quote, that the gallery is no longer the primary exhibition space, the internet is. And in that sense, you know, what it means is that often you have a gallery opening where reviewers come or visitors come, they take pictures and then they put it on the internet. And at the end of the day, more people see that images on the internet, so the exhibition on the internet, than actually in person. And I think one of Matej's ideas was to kind of scrape the actual exhibitions themselves and just put and just generate images of generate images that that people can see on Instagram. And now back to the more let's say back to the machine learning, let's say. So this implementation of this project consists of two modules, let's say. One is the module that communicates with Instagram. It's a downloader and uploader. It doesn't use official Instagram API, but we'll get to that. And the other part is the generative adversarial training and image generation. And here you can see a little bit of progress, a little bit of how the network was progressing as it trained. And it's interesting that we've started as with a pre-trained network, and that was a network pre-trained to generate faces. And then we kind of showed it our new data, which is this images of exhibitions, and it gradually gained more detail. And this is an image, for example, from the latest checkpoint, and you can see how everything changed. Also, what is not shown here is that variety changed a lot from the beginning. Pretty much all images looked like that in first 10% of training. Later, then they became more diverse. I want to first say a few words about Instagram Scraper, not because it's from an implementational point of view. I think it's very simple, but Instagram really doesn't want you to scrape images from their platform in large quantities. And the first thing we tried was public Instagram access, and this Instagram figured out quite quickly that something fishy is going on, and they simply blocked the IP address. Then we've tried Instagrapy or Insta. Yeah, you know how what the pun here is. Which also turned out where you have to log in, but it turns out that when Instagram knows who you are, they just delete your account. And at the end, we sell with Instagram clones that allow you to scrape Instagram all you want, because they use some kind of proxy to actually get the images from Instagram, and this still works. For example, one of these Instagram clones is pizzuki.com. And how this scraper works is we simply scrape the new posts from followed Instagram accounts on a daily basis. And this is one script, and the other script is we post an image 1 to 3 times a day. And this is pretty much it. It's really very simple. On the other end, we have generative adversarial network training, which happens on Google Colab, because we didn't have strong enough hardware to actually do it on any of our personal computers, and it has to run like all the time. It's this network is still training because it's receiving new data on a daily basis. And simply what happens here is you upload newly obtained images to Google Drive, and then you run the Google Colab notebook that generates images first, and from these images, some are randomly chosen for upload, and it continues GAN training from the latest checkpoint. The neural network, the generative adversarial neural network that we use in this project is StyleGAN, and StyleGAN had its own kind of history. In our case, we use StyleGAN 2 minus ADA, but it started way before that. And what really StyleGAN is a generative adversarial network that enables you to kind of manipulate images in a very linear way. So the previous example where I was showing you the editing in latent space, that uses StyleGAN particularly because it doesn't use this fully entangled latent space, but that is usually denoted as Z. You can see it here, but instead uses W latent space, which is kind of a transformation of this original one. And then StyleGAN 2 kind of redesigned how these latent vectors are fed to the network. And this third step, I think, was fairly important because you can augment images. It enables you to augment images so that the StyleGAN trains faster, and that's very useful when you don't have a lot of data. And recently, StyleGAN 3 came out, which is invariant to transformations and enables generating smoother videos. Note that I didn't do any of the development of these things. This is all NVIDIA's work. We simply used the code repository for StyleGAN 2 ADA, and it turned out to produce very stable outputs, and it's still working very well. Lastly, I want to talk about how all this, talk a little bit about how all this is implemented. And in short, if you want to do machine learning, or if you want to do work with neural networks, you usually want to use a GPU. And there are two very, I think, known libraries that most researchers, or even I, use. And one is PyTorch, and the second one is TensorFlow. They both offer capabilities like automatic differentiation, or calculations of gradients, some kind of wrapper functions for some very complicated tasks. But in this particular project, we were using PyTorch, so I'm just kind of going to concentrate on this from now on. And I first want to say a few words about the typical PyTorch pipeline. So just so you get kind of a feel of how all this might work, how training performs using a high-level library. And first of all, it's kind of similar to NumPy, for those of you that have worked with it before, in the sense that it's it's just very similar. I don't know how to describe it. It offers, like I've said before, automatic differentiation, and it abstracts away many implementational details. Some of the main components of the code you'd want to use for training a neural network, and this is not particular to generative adversarial networks. This is way more. This is like for neural networks in general, and here I'm presenting to you like a particular case where you would do where you would want to classify classify some input data. You'd first need a data set, and Torch Vision is one place to look for a data set. MNIST, here I used MNIST, which is a handwritten digit data set. You would need the data loader, which splits this data set into batches, because the whole data set can't fit on the GPU. You have to kind of do things in smaller quantities. You would need to define the model, which is our neural network. Here, VGG is used, which is like an off-the-shelf computer vision model, and it's put on the GPU. Then you have to define your loss. Even if you don't know what actually happens when you call this cross-entropy loss, it's sometimes just enough to do these kinds of things, just to know in which case you have to use what kind of loss. And here we are using cross-entropy loss, which is very similar to one part of how generative adversarial network is trained. Lastly, you have the optimizer, which actually performs steps in this multidimensional environment to minimize the loss. And you simply have to give it the parameters and the weights, so it has something that it changes. Then you have this double loop. On one part you have, so the first loop is kind of goes through the whole data set, and going through the whole data set is called epoch. And you usually go through the data set multiple times. So that's why you have n epochs here. And then you sample batches, which are X and Y, corresponding to input data and labels respectively. So you sample batches, you put them on the GPU, you obtain predictions from the model based on the inputs on the X. This would be, in this case, images of handwritten digits. You compute the loss. This is like, in this case, you can imagine this to be like a difference between what the true labels of the presented data are and what our predictions are. And then you kind of call these three functions together, where you kind of delete the gradients from previous rounds or previous iterations. You make a backward step. This actually backpropagates the gradients. It calculates the derivatives of all weights, and then you perform a step with an optimizer. And this is pretty much it. Now, I see that I'm at the 40-minute mark, and as I promised in the beginning, I would be perfectly fine with having some kind of discussion, or I can move on and show you pieces of code how generative adversarial network, StyleGAN, which was used in the project I talked to you about, was implemented. You tell me how willing are you to listen to my rumbling for another few minutes, or you can just ask questions and we can do it in a completely non-structured way.
I think we could go another couple of minutes with code samples, unless anyone disagrees. Right in the chat. I do see we have one question so far, so that's not going to be, it's not going to be going for too long, I guess. So, I mean, I vote for you going over the code samples like somewhat quickly, and then we'll see where we go.
Sure. The thing is that when I was preparing the presentation, I figured out that if I show you, for example, something like this, it's even hard for me to, maybe I have to enlarge this. It's even hard for me to kind of find what I would like to tell you, because these files are very long, and the particular implementation of StyleGAN that we used has a lot of like additional code that is just just hard to, that I think would just confuse a lot of people that haven't worked with PyTorch before. So I instead decided to use a non-official implementation of StyleGAN, which I think is much more concentrated around the important parts. And let me see if I can make this a little bit larger. Oh, yes, nice. Okay, so I guess you can all see that. So very quickly, keep in mind the short snippet that I showed you on the last slide, because this is fairly similar. You have to define your neural network. In this case, it's StyleGAN. You have to define your data set, and then you call some function, which is StyleGAN.train, that iterates just like iterates through the data set, just like it was in my example on the previous slide. So here's the train function, and before that, we first have to see how the StyleGAN is defined, right? Because that happens before training. You can see you have your generator here, your discriminator here. You have here you define both optimizers. It uses an Adam optimizer, but that's not important. And you have to set up loss, which in this case is binary cross entropy with logits loss. Now it doesn't maybe particularly matter what that means. It implements in essence the equation that I showed you, the only equation I showed you on the slide. But what I would really like to point out is this minimax game that I told you about before. And you have like two aspects of this, of what we want to achieve, right? You have one aspect that centers on the discriminator and the other one that centers on the generator. And here, let's start with discriminating because I think it makes more sense. You have real samples and you have fake samples. That's the first thing. And real samples are from the data set, while fake samples are generated by the generator. And you get some prediction about how real these real samples are and how fake these fake samples are. And then you can see here you have this criterion, which is our loss, and you simply put these are the real predictions, how real the real inputs are, and these are ones. So in essence, what this criterion does is it kind of minimizes the difference between these predictions and ones. So in essence, what we want to do is have these predictions as close to one as possible. While for the fake predictions, we do exactly the opposite. When we are training the discriminator, we want them to be as close to zero as possible. And this is then simply summed up and divided by 2 to kind of get a balanced loss. While when we train the generator, we also have the criterion, but here we have these fake samples and these predictions about how real, what the probability of them, what the probability is that they are real. And here we want this criterion. So here we want them to be as close to 1 as possible. And this criterion measures the difference between these predictions from the discriminator about fake samples and ones. And this is really on like another level. This is really the core of how StyleGAN gets trained. What I would like to show you, the last thing is the main loop that I also had on the slide before, like in my short example, where you also have epochs, you have batches, and you generate some latent vectors, and then you optimize discriminator, and internally in this function, this loss that I told you about before gets called, and then you optimize the generator. You kind of repeat this until both of them converge. I think this is enough about how StarGAN is implemented. I just wanted to show you essentially how in practice you would implement a loss, because I don't know, I just think it's an interesting detail, and it's really why all this is powerful. You probably haven't noticed I talked about PyTorch a lot, because PyTorch is hidden in some different levels of this computation. But for example, where the neural networks are defined, but I think unless somebody else is explicitly interested in this, I think I can just admit it. And yeah, I think I'll stop here, and any questions, I'm happy to answer them.
Yeah, let's start with the one we have in the chat, because I think it's kind of like really connected to what you were just saying, because you mentioned PyTorch. So someone was asking, how do you feel about Keras as opposed to PyTorch?
I've used it for some time, and if I'm not mistaken, I'm not using it anymore because I just often don't have a use case for it, since I'm using PyTorch, and the level of abstraction in PyTorch is quite similar to Keras. But I think the main difference is that kind of Keras is built on top of TensorFlow, the framework that I mentioned here. And TensorFlow is like really low level, and Keras enables you to perform some more, to call some high level functions. For example, you can just call, I think, fit or something like that, and it trains the network and so on. Now PyTorch kind of provides both. Maybe not on this. Maybe the high level access is not on the same level as in Keras. You still have to do some things a bit more manually, but it's good enough for me and for what I use it for. That would be my answer. It's not the direct answer, I know that. It's not that easy to say how I feel about that.
Okay, thank you. Do we have anything else regarding questions or comments? Anything in that realm?
And yeah, by the way, I see somebody commented in the chat VS Code GAN. Yeah. If you didn't know, you can open any repository on GitHub just by adding. I have it here. Just by adding one S to the so GitHub1s.com changes any repository into a VS Code interface in your browser, and it's super useful because you can load extensions. You can do you can do a lot of things. Yeah, just like you would actually, if you have this.
Like, I think I forgot. Like, I commented that, but I think I forgot about this specific tidbit. That's really useful, actually. Thanks.
Yeah.
Okay, well, if we don't have anything else, I kind of I guess I could have a question, but it's maybe not specifically machine learning related. So I debated like even asking that, but if there are no other questions, maybe I'd like to take a step back and just, because I was wondering, I'm familiar with this project, and I was wondering just generally, since what were like some other challenges that you ran into technically with this project? Because I know you mentioned like the problem of scraping Instagram and stuff, and I know that's not what this talk is about, but it's just something that's been on my mind since you first introduced the project in Osmoza. Like, what were because I know that Instagram is really against that, and yeah, I know that you really do need to have a substantial like data set. So that's definitely important, the scraping part as well.
Oh, just a second. Okay, can you hear me?
Yeah.
What is going on? Music is playing from my headphones.
Yeah, we can't. Unfortunately, we can't hear it.
Okay. So let me answer your question. The by far the biggest problem was how to obtain the data, because I think me and Matej were kind of having like 3 iterations of the scrapers and how they should work, and trying out different libraries. So that I think took the most time out of all things. Beside that, I think using Google Colab in sort of like a production environment, in a sense, not just to play around with, as something to daily train the model and continuously train the model, is also not the most elegant thing ever. For example, you have to log into Google Drive every time you start the notebooks, so you can upload the checkpoint, the latest checkpoint, for example. You have to kind of do all the communication through Google Colab, which is I don't know, it's a bit cumbersome, and I would definitely prefer running this on some kind of local machine. But yeah, it was more like, it was not a challenge like an Instagram challenge where you would either get the data or not. It was more like finding like the most elegant way to daily train the model. And Matej, I think, still every day has to press like execute all cells so the StarGAN starts training.
Okay, so it's not all automated.
That's the level of
Yeah.
cumbersomeness. No, it's not all automated, not at all.
Yeah, but a large part is, yeah.
Yeah. And I've just recently started looking into how to kind of automate Google Colab jobs. And maybe if I figure something out, I can have a talk in a few months.
Yeah.
If anybody would be interested.
Yeah. I see there's like a couple of interesting components in this project. So what was the API you said you used in the end for scraping?
It's this one. Am I still sharing my screen?
Yeah.
Yes, I think I am. It's
I just think it's a common problem. Everybody wants to scrape Instagram, but Instagram doesn't want to be scraped, right?
Yes. Is this gonna work? Yes. So this, I think this is the most up to date. It uses an unofficial API because official Instagram API doesn't let you do much unless you're a brand or something like that. Or I don't know how they're called on Instagram, but this is an unofficial Instagram API, and it worked quite well. It recently started to. I think this just recently started to prompt password changes on your Instagram account every now and then. But yeah, considering it allows for I don't know, obtaining all your account, all the accounts you're following, and all the images you posted, commenting, and so on. It's actually quite powerful if you just don't do it on a too large scale. But yeah, this, and then there is and which is like an Instagram clone. You can, for example, search here for account. If this is going to work now. Well, anyway, you can search for an account and scrape it all you want. They don't stop it at all. This is like a clone, and it has all the images from Flat Gaze right here, and at the end, for actually obtaining data, this was used, or this is still used, and this API is just used to get the accounts one is following.
Okay. Yeah, I see that. That's interesting. And generally, I would recommend everybody check out this project because it's, like I said, it's interesting from several different points of view. And yeah, I don't know. I guess that's it.